Okay, we're going to have a look at what we need for the third assignment for Unit 27 on the Level 3 BTEC Extended Diploma in Engineering. Right, so perhaps the easiest way to tackle this is to start from the criteria and we'll work backwards from there. So we'll tackle each pass criteria in turn, and then we'll look at the merit and distinction criteria and the pass criteria that goes along with that. And each of those will be its own separate video. So for P5, it says calculate the actual stress produced in a rigidly held simple structural component when subjected to a combination of axial loading and temperature change. So what does that mean? That's quite a lot to unpack there. So axial stress, stress along the axis. So if we have a long thin bar, it will mean we hold the bar at each end and we either pull or we squeeze. Yeah? So you can see here in the diagram I've got a compressive load acting along the long axis, or in the same direction as the long axis. It could be a tensile load, in which case I'd be pulling the bar apart at either end. Okay, so when subjected to a combination of actual load and temperature change. Now, why is temperature change mentioned in this for loading? Well, the question we need to ask is what happens to materials when the temperature changes, and the answer is to a greater or lesser extent, they grow or shrink. So generally, as things get hotter, they expand, and as things get colder, they contract. And we can see this in everyday action as we drive over a bridge, a particularly big bridge. You'll hear a as you go over the bridge, and that's as you drive over what's called expansion joints in the bridge, and there are little gaps in the bridge that allow the bridge to expand and contract over a range of temperatures. So the weather outside could be anything from, I don't know, lately -5 up to a scorching 35 degrees in the height of summer. So that can lead to a good few millimeters or more of change in length, depending on the size of the structure. So that's the reason when you're on a railway, when you're on a train, you hear the that's the gaps in the railway line, which allow for expansion and contraction, so the railway lines don't buckle. I think more lately solutions have been found that allow more smooth running and for the expansion and contraction. But there we go. So things get bigger when they get hotter, and they get smaller when they get colder. And what we're saying in this question is it's so rigidly held. So we've got this beam here, and we're saying, well, we're clamping it at either end, and we're not allowing it to expand or contract. And so what happens if we have a change in temperature and therefore a change in length? So this beam here is going to try and change its length, but it's unable to, so it's going to produce a force. It's going to push against the clamps that are holding it in place. So what is that force? All right, so that's where we're going with this. So how do we unpack this? Well, it's going back to our old friends stress and strain. So you may remember that we've got three equations for that. We've got Young's modulus equals stress over strain, and Young's modulus is represented by a big E, and stress is a sigma, little sigma, and strain is little epsilon. And then we've got stress equals load over area, so load is a force, so F over A, and strain is a change in length divided by the original length, and you'll see that as delta L. You might sometimes see that as X, small letter X there, instead of delta L, change in length, over original length L. And it's probably worth remembering at this stage that strain is dimensionless, because we're dividing meters or millimeters by meters or millimeters, and so they cancel out, and so it's just a ratio of lengths essentially. Stress is in load over area, so that's force divided by area, so that's newtons per meter squared, and Young's modulus is the same because strain has no dimension. And you might also remember that Young's modulus is useful because it marks the stiffness of material. So the stiffer a material, the more load, more force we can put on it, and the less it will bend. So that's a useful measure. So we're just going to have a little sidetrack and refresh our minds on how E relates to actual real world, the real world, and then we'll swing back. Okay. So we can see here a graph of a piece of mild steel which has been subjected to a tensile load, and as we go up the stress strain graph, so we're increasing the force. Remember, stress is force over area, and we get this nice linear line. So the force is proportional to the extension. And what we mean by that is that if we put on, say, 5 newtons, we extend, for argument's sake, 5 centimeters. If we put on 10 newtons, we extend 10 centimeters. So, you know, kind of behavior we expect from a spring. Yeah, when we use a Newton meter, that's what we're seeing. We're seeing, you know, we put on a certain amount of weight and it moves down the scale by a certain amount. So that's what's happening in the straight line area. And this is called the elastic region, because that means if we take the load back off our piece of material while it's in this elastic region, then it will go back to its original length. Just like if we stretch an elastic band and we let go, it will go back to its original length. Yeah. After this point, after the yield strength point, then we're in what's called plastic deformation. So in this plastic region, what happens if we take the load off? It does not go back to its original length. Okay. The top of the curve here is the ultimate strength, ultimate tensile strength, and that's the maximum load it can make. And after this, we get narrowing in the middle called necking, and that eventually leads to failure of fracture. So where does that give us? Well, we know that Young's modulus is stress over strain, and we've got a stress strain graph. So stress divided by strain, well, you know, as you know from your calculus module, that's dy by dx. So actually, Young's modulus is the gradient of the stress strain graph. So that's worth noting, and they've called it the rise and the run here. And so Young's modulus is the slope, the gradient of our stress strain graph. So that's good. This video is well worth a watch. Obviously, I'm not going to put that on for 8 minutes, but I have put a link to it in Pearl Trees, and we actually see a tensile test happening and the graph being made as we go. So, as you know, you can find these resources under the Resources tab in your Teams, among other places, and that's the YouTube video I've just highlighted there. We've got a couple of YouTube videos and an explanation there of what's going on. So if you want to just recap and refresh your memory on what's going on with Young's modulus and stress and strain. So returning to our calculations then, Young's modulus, which we've just said is the gradient of the stress strain graph when we're doing loading a piece of material, is our big E. Stress is load over area, force over area, and strain is change in length over original length. So I just gave it away there. Where does temperature come into all of this? How do we integrate temperature into all this? Well, essentially for this pass criteria, we're not asking you, you're not being asked to do anything new from what you did last year in Unit 1. In regards, so you should be familiar with these 3 equations. We're just extending this a little bit now, and the change in length, our delta L, is coming from this equation here. Okay, so our delta L is coming from this equation here. L equals alpha times by delta T times by L. So what's that all about? Well, if we accept that when there's a change in temperature, there's a change in length. So for argument's sake, for 1 degree change in temperature, temperature goes up by 1 degree, our structure extends by 1 centimetre. Temperature goes up by 2 degrees, our structure extends by 2 centimeters. Temperature goes up by 3 degrees. So you get the idea. So we need to know, well, what's the change in temperature? Okay, so there's the thing. Yeah, and we need to know our original length, because otherwise, how do we know how much it's extended by? So, yeah, and that leaves this alpha. This is a Greek letter alpha, small alpha. What's that? That's something called the coefficient of linear expansion. Okay, and that tells us how much a material expands by per degree per unit length. So for each meter, the material might expand a millimeter for every degree temperature. Yeah, so that's why we need the original length. So we need to multiply this value by a change in temperature and our original length, because this value tells us how much things change for each change in degree per length of original length. All right. And all we're doing for this first question is we're taking this change in length. There should be a delta there, shouldn't there? Let's just make that so. Yeah, this change in length here goes into this equation here, and then we're just using those familiar stress-strain equations in this case to work out the force. Okay, so shall we step through an example to see how that works? Okay, I'm glad you asked. So here's our question. What is the change in length for a beam 20 meters long, made of steel starting at 10 degrees C and ending at 30 degrees C? Alpha equals 11 times 10 to the minus 6. Now, just a quick word about alpha. The value of alpha, the value of the coefficient of linear expansion is each material has its own value. If we weren't given that, or if we want to query that, or we need to find that out, then we can look that up on engineering websites. So, for example, we can see here a list of values of the coefficient of linear expansion. This is a cut down version that I've put together, and that's taken, as it says there, from the engineer's toolbox, which has a much more comprehensive list. You can also find it in engineering books in your library, and other web resources are available. There we are. There we can see expansion of a railway track causing some buckling there. Okay. So we've found our value of alpha. Well, we've been given a value of alpha. Beam diameter is 150 millimeters. So as soon as we're seeing diameter, we need to be thinking circles and cylinders. If the beam is held at each end, what is the force? Okay. So the first question we need to answer then, what's the change in length? Okay, we've got a 10 degree start and a 30 degree finish. So that's an obvious change in temperature of 20 degrees. And what we've got to remember is that because it's a change in temperature, we don't have to convert to Kelvin, because 1 degree change in centigrade Celsius is the same as 1 degree change in Kelvin. So 20, change of 20 Kelvin, change of 20 degrees Celsius is exactly the same. Okay, so change in length, we can answer that question straight away. There's our coefficient of linear expansion. Yeah. There's our 20 meters long, and there's our 20 degrees change in temperature. Okay, and there's our answer. So yeah, it's 4.4 millimeters. That's not inconsiderable. That's that's something you can actually see on a ruler. Is that 4.4 millimeters, nearly 5 millimeters change in length? It's not much for over 20 meters, you might think, but if you don't allow for that expansion and contraction, then you can have problems. Right. So from here then, it's all a question of just plugging these numbers into our three favourite equations. So it might be worth writing down what we know and what we don't know, if that helps, and write down your equations, because that might help you think your way through them. So if you've done that, if you find that helpful, that's absolutely the way to go. I would always suggest, if you're doing assignment work, always make a list of what you know and your equations, just to help clarify your thinking, and help your teacher know what's going on when they come to do the marking. Right, so we start then with stress, strain, strain. There we are. We start with strain because we know the original length and we've just found the changing length here. Okay, so we've put those numbers in. I'm keeping that in meters, so I could also have written that as 4.4 times 10 to the minus 3 to keep it in millimeters, to keep it in meters, sorry. And obviously the 20 was already in meters, which gives us a strain of 0.00022, or 220 times 10 to the minus 6. Now, when reading this off your calculator, be careful to make sure you make note of the minus 6 or the powers. Okay. So now we've got our strain. We've got our Young's modulus, and again, just as for the coefficient of linear expansion, our Young's modulus is unique for each material, and if it's not given in the question, then we can either remember that steel has a region of 200 to 210 giganewtons per meter squared, or gigapascals. Pascal is Newton per meter squared, more often used with pressure, but sometimes used as we're talking about stress strain. Or you can look that up, but I think are we given that in the question? We're not given that in the question, so you might have had to look that up. So Young's modulus, we've looked that up from Engineer's Toolbox or other source, Young's modulus of materials, and there we go. So that's where we get that value from. Okay, so we know our Young's modulus, and we know our strain, and so we know that Young's modulus is stress over strain. So again, I'm just putting the numbers in here. Yeah, Young's modulus, strain that we just calculated, rearrange our formula, and then that gives us an answer here. Okay, so 44 times 10 to the 6 newtons per meter squared, or 44 meganewtons would be an easier way to write that. Yeah. Okay, so the final thing that we need then is, if we're looking for the force, which we are, then we're nearly there, aren't we? We're nearly there. Yeah, we've just found out this, and we can calculate the area because we've got the diameter, and so we can find our force. So let's have a look at that. Now, area of a circle, that's the one that you're all familiar with, pi r squared. But we can also use this formula because this is also true, pi d squared over 4. Now, personally, I often get myself confused with diameters and radiuses. So, if something's given to me in a question with a diameter, I'll use this. If something's given to me as a radius, I'll use this, because, I have before, and probably will again, put a radius in the equation where I should put a diameter, or a diameter where I should put a radius. So, as we've been given a diameter, I'm going to use this equation. Okay, so there we are, pi d squared over 4, and there's our answer. Yeah, always make sure you do the square. Yeah, I often forget to do that as well. Okay, so now we've got our area. So now we know our stress, as we calculated that here. We know our area, and now we can find our force. So we've put our numbers in our equation here, rearranged it here, and that gives us our final answer there. Hopefully that's clear and step by step for you. Any questions, just drop me a direct message on Teams, or if you're not at the Manchester College, I might even answer questions in comments. Okay, thank you very much. Bye.